Good morning, everybody. In this session, let us continue with few more important recording devices. First one is called as LVDT type recorder. So first let us try to understand what is LVDT, then we'll go for LVDT type recorder. LVDT is nothing but linear variable differential transformer, LVDT. So the main purpose here using an LVDT is to measure the displacement or movement of any object, to measure the distance of movement of any moving arm. We are going to use LVDT. So since it involves a transformer, it has primary and secondary windings. It has a primary winding which is connected to the AC input, and then it has secondary winding which is divided into two equal halves, and both the secondaries are connected in series opposition. Series opposition means the so if you consider the starting end and the finishing end of the coil of the secondaries, they are connected in reverse fashion. That is, finishing end of one coil is connected to starting end of the other coil. Likewise, it is connected in series opposition. Finishing end of one coil is connected to finishing end of the other coil. Starting ends are tapped out. So here, since we are connected this in series opposition, the EMF that is induced E0 across the output terminals are ES1 minus ES2, where ES1 is the voltage induced in the secondary one, and the ES2 is the EMF induced in S2. So the effective voltage available at the terminals are ES1 minus ES2, difference between ES1 and ES2. And now here we have the core in between the primary and secondary windings, and then the moving arm whose displacement has to be measured is inserted inside this core. Thereby, whenever the moving arm moves, the core also is going to move accordingly. So now we have three possibilities. When the core position is in the center, when the core position basically is at the center, there will be equal flux linkages to both the secondaries. So EMF induced in both the secondaries will be equal. So E0 will be equal to 0. So you can see here E0 is equal to ES1 minus ES2, which is equal to 0. There will be equal flux linkages between ES1 and ES2. Equal flux linkages, and voltages ES1 and ES2 will be same. Then the other position is left extreme position of the core. When the core is in the left end extreme, at that point of time, there will be more flux linkages with the secondary S1 compared to S2. So obviously ES1 will be greater than ES2 and E0 will be positive. On the other hand, whenever the core is in the right extreme position, there will be more flux linkages in S2 compared to S1. So ES2 will be greater than ES1, thereby E0 will be negative. So ultimately, the magnitude of E0 measures the displacement of the moving arm. So if we are able to measure this E0 value, that magnitude of the that E0 itself is equal to the displacement of the moving arm. So now let us see LVDT recorder. So using LVDT, whatever we have seen so far, we could measure the displacement in terms of voltage. Now we should be able to record the same. That is nothing but done by LVDT recorder. So let us see the arrangement here. We use two LVDTs here, LVDT1 and LVDT2. Both the LVDT secondaries are connected in series opposition, as we have seen earlier. Earlier we have seen one LVDT. Here we are seeing two LVDTs. The moving arm which is undergoing displacement is inserted in core of the first LVDT, while the core of the second LVDT is driven by a servo motor, and the same servo motor is mechanically coupled with the pen that drives on the chart. And we have an AC amplifier to produce suitable amplification of the signal to drive the servo motor. So initially, the core of LVDT2 remains stationary, and core of LVDT1 also remains stationary at the same corresponding positions. That means if core of LVDT1 is at the center, core of LVDT2 is also at the center. This is what happens initially before the measurement. Or both the cores may be in left extreme, or both the cores may be in right extreme positions. At that point of time, the effective voltage E1 and E2 will be the same. So since E1 and E2 will be same, there won't be any input to the AC amplifier, hence servo motor will not rotate. Now if there is a displacement that has to be measured, then the core of LVDT1 undergoes a change in the position. That is, the moving arm here changes its position from the initial position. So once it changes its position, our E1 will change with respect to E2. Now E1 will not be equal to E2 anymore. Whenever there is a difference, the difference will be given to the AC amplifier. AC amplifier amplifies the signal and drives the servo motor. Servo motor now begins to rotate. Since it is mechanically coupled to core of LVDT2, the core of LVDT2 also undergoes movement, and this servo motor is going to rotate as long as it gets the input, and the input is given by AC amplifier. AC amplifier is going to work as long as E1 is not equal to E2. So thereby the servo motor is driving the core of LVDT2, and this driving happens until E1 becomes equal to E2. That is, this core also attains the same position as that of our moving arm core in LVDT1. Then once E1 becomes equal to V2, motor stops to rotate, and then AC amplifier will also not work now, since it will not get any input. It will not drive the motor. So during the movement of the servo motor, when E1 was equal to when E1 was not equal to V2, it was also mechanically coupled to the pen on the paper. So the displacement now is marked on the chart paper. So this is how LVDT recorder works. Next, circular chart recorder seems to be very simple. So I'll be taking the next one, which is more difficult one. XY recorder. See, generally whenever we go for plotting any graph, it will be any signal with respect to time. But sometimes we plot a signal with respect to another signal. That can be done using XY recorder. So here XY recorder plots the variation of one parameter with respect to another parameter, not with respect to time. So we have signal A, we have A here, which is nothing but the attenuator. We have X input, we have Y input. X is one signal, Y is another signal. Attenuator, as you know, will attenuate the signal, that is reduces the amplitude to suit the requirements of the next block. We have balance or error detector, which continuously compares the reference or the reference source along with the given input, and then whenever there is a difference, it will drive the output and it will be fed to the chopper basically converts DC to AC. That will be fed to the servo amplifier, which drives the servo motor, and the servo motor here is connected to a pen that controls the horizontal movement of the pen, and in the other channel we have another servo motor which is going to control the vertical direction of the movement of the slider which has the pen mounted on it. So here, when both X and Y inputs are given together, there will be horizontal as well as vertical movement simultaneously, and then that will be recorded on the paper. Servo motor A is going to be driven because of the input X, and servo motor B will be driven because of the Y input. Thereby both the pen as well as the slider mechanism will move vertically as well as horizontally. Thereby the pattern X versus Y will be recorded. And we have the specifications: accuracy plus or minus 0.3%, speed 1.5 meters per second, sensitivity 10 microvolts per mm, chart size generally will be 250 by 180 mm, and applications to plot the speed torque characteristics for any motor, and then also to plot stress strain curve. Then again, since digital tape recording happens to be a simple topic, I have skipped this in the video recording. Next I'll be going to UV recorder, which is ultraviolet recorder. So here in this ultraviolet recorder, we have UV light source, which is essentially a UV bulb, and we have one fixed mirror over here, which is fixed mirror 1, and then here we have a movable mirror, and there is a spring here which provides the damping. This is a movable mirror which can move in either directions. It can rotate, which is mounted on the shaft. Here we have permanent magnet, and we have moving coil over here, and the direction of movement is being shown. We have another fixed mirror too, and finally we are having the photosensitive chart here, which is sensitive to light. Whenever light beam falls on this light, it gets recorded, pattern gets recorded. Now again, this also works on D'Arsonval's principle, that is, current carrying conductor placed under the in the influence of magnetic field experiences a force. So this moving coil, when it carries current in the presence of magnetic field, experiences a force, and torque will be developed. Thereby it undergoes rotation. Then the mirror also is going to rotate. So now initially uh, there is no current flowing through the moving coil. At that point of time, UV light source will provide the light beam, which will fall on the fixed mirror 1, gets reflected onto the movable mirror. Again it undergoes reflection, and the reflected beam falls on fixed mirror 2, and finally due to the reflection by fixed mirror 2, light beam will fall on the chart or the light sensitive paper. Now whenever the unknown signal is applied to the moving coil, because of D'Arsonval's principle, it experiences a torque, and then the movable mirror tends to rotate. It tends to rotate in either clockwise or anti-clockwise direction. Thereby, the light beam that is reflected from the fixed mirror 1 undergoes deflection. Thereby, the position of the light beam on the movable mirror changes, and the same will be reflected onto fixed mirror 2 and onto the paper. So thereby, whenever the movable mirror goes on rotating, the light beam pattern will fall at different positions on the paper. So the changes will be plotted on the paper. So due to the variation of the signal, the pattern of UV beam falling on the chart also keeps on changing. Thereby, the variation is plotted. This is the concept of UV recording. So this finishes UV recording. So with this I am concluding module number 5.